Greetings and welcome to a new video about a DC shunt motor example. This will be our example number 7. In this example I will again discuss another problem using a DC shunt motor. So let's look at our example. A DC shunt motor has a terminal voltage of 275 volts. The armature resistance is 0.8 ohms and the field resistance is 250 ohms. We also have, in addition, two conditions, one at no load, then the shaft speed is 125 radians per second, and also the armature current is given, that is 3 amperes. But at full load condition, the terminal current is 29 amperes, and also the flux is 6% less than in the no load condition, that's due to the armature reaction. So we need to also take this into account. That will be discussed shortly. Okay, the question in this example is calculate the full load shaft speed. It is given by omega sub m by the full load FL. Okay, let's look at our solutions. How do we work this out? Again, we start with our model, and that is shown here for our DC shunt motor. This is the field part, this is the armature part, and also the back EMF part, and we have here the terminal voltage and also the resulting terminal current. Let's first look at the no load condition. No load condition, we have for the field the situation as follows. We know that the field has exact same terminal voltage as also the armature, so we can say the field voltage is equal to the voltage across this RF plus the voltage across this inductor. Now we know we work in this DC system, so we know that the reactance of this inductor LF will be 0, and then we have actually this simplified expression to calculate the field current, and that is just 1.1 amperes, and this is also true for full load conditioning that will be discussed shortly. Okay, we have now our field current. Let's also look at the armature part. Armature, again, it's a similar form. We can set up the equation using the Kirchhoff voltage law. What we have is the terminal voltage equal to the voltage across this resistor of the armature, across the inductor of the armature, and also the back EMF. This is shown here, and then specifically I have also shown the no load conditions for the current and also for the back EMF. And again, in a similar form, we can say that inductor will be 0, since this is the inductor reactance will be 0, since this is a DC system. So we have then this condition, and we can just substitute the values given in this example. We have 275 for our terminal voltage, 3 amperes for our armature current in this no load condition, and also 0.8 ohms for our armature resistance. Now if you do the calculations here, you will get for our back EMF voltage for this condition of no load is 272.6 volts. Okay, this is what we have. We continue with actually the calculation of the motor constant also, because that is required for no load and also the full load conditions. This is the general expression, and again specified by the no load. This is the motor constant, and also this is the shaft speed for the no load condition, and that is given. That's 125 radians per second. I know this from the analysis here, and I can now calculate the motor constant, just substitute the given values. We have now 2.181 Webers. Alright, now using this we can just move on to the full load condition. Okay, in our full load condition we also need to set up our equation for the armature and specifically for the full load. And again we can set up the equation by using Kirchhoff voltage law. Terminal voltage is equal to the full load back EMF voltage plus the voltage across this RA at full load condition, and also the voltage across this inductor at full load condition. But again, the reactance of this inductor will be 0 in DC system, and again I lose this part. So I'm left with this expression. Now we have, this is not known for the full load condition. This is also not known. We know of course the armature resistance and also the terminal voltage. So we have actually two unknowns here to continue. You might ask, why do I need this expression? In order to go to the full load shaft speed, I have the back EMF. I require the back EMF for our full load condition. because the no load condition also expressed this for the shaft speed, so I need the specific value for the full load condition, so I need this value. But before we move on, I need also the armature current. So I know also in the condition of the full load that the terminal current is given, which is 29 amperes. So I can say the terminal current here is the summation of the armature and the field. So that is then here, and again specified for full load. Full load terminal current is equal to the full load armature current plus the full load the field current. But full load field current will stay same. That doesn't change for no load or full load. So we have this still as 1.1 amperes. So we can say 29 for our terminal current at full load is equal to the armature current plus the 1.1, and also in the no load condition exact same as the full load condition for the field current. Then we can calculate what the armature current must be at full load condition, which is then here 27.9 amperes. Now I'm now very close because I can now use this expression. Now moving on and then express this actually in using this back EMF, setting up the equation just for the full load condition of course, and then substitute the values because this is then 275 again. This is now the new armature current, which is actually increasing from 3 amperes to 27.9, still 0.8 ohms for our armature resistance, that won't change. Then I have now the new value for my back EMF, which is then 252.7 volts. So I actually decreases from 272.6 volts to this value. Now I'm now very close because I can now use this expression again to calculate the omega for full load. But now I have to be very careful. I already said that in the beginning, the flux is less by 6% compared to the no load condition. What does actually that mean? If you look at the motor constant expression, there is the flux symbol here. That means actually there's also a relation to the flux. In this case, I have 6% less flux. That means actually the following. The expression for our back EMF now is again using the motor constant we already calculated, but it is now 6% less than in the no load condition. So the full load condition motor constant will be then 0.94 times the motor constant for the no load condition. This is very important. So if this is 6% less, I have to multiply this by this scaling factor. And now I have the full load shaft speed. Okay, I can now move on. Having calculated, of course, the value here, I can just substitute this in here, and I have now the values for the back EMF and also the scaling here due to that flux reduction of 6%, and this is now our motor constant also in the no load condition. If I now just substitute the values, I will get 123 radians per second. So I decrease actually the speed from 125 radians per second to 123 radians per second. And that's now the situation for this exercise by looking at the no load and also the full load situation for the DC shunt motor. Alright, this concludes this example number 7 about the DC shunt motor. If you have any questions, please let me know and I will try to answer them as soon as possible. Thanks again and see you next time in another interesting video.